You've spent hours, maybe even days, hunched over your keyboard, meticulously crafting the perfect 3D model. It's a masterpiece. Every curve is flawless. Every detail is razor sharp. You can already imagine holding it in your hands. So you export the file, upload it to an online 3D printing service, punch in your credit card details and lean back, filled with the pride of a creator. A week later, a box arrives. You tear it open with excitement, and inside is a stringy, warped, unrecognizable blob of plastic. A $50 piece of modern art that looks like a bird's nest after a hurricane. You contact customer support, confused and frustrated, and you get the soul-crushing reply, "Sorry, there was an issue with your file." That exact scenario is the silent killer of thousands of brilliant ideas every single day. And it's built on one massive lie we've all been told. That if a model looks good on your computer screen, it will print perfectly in the real world. That is fundamentally, dangerously wrong. Your computer screen is a magic box of illusions. It has no gravity, no material science, no physics. It can display a wall that's infinitely thin. It can show two objects occupying the same space. In the digital world, anything is possible. But the second you hit that print button, your design crashes headfirst into the unforgiving laws of reality. And if your file isn't prepared for that collision, it will fail. Every single time. This is the bridge. This is the guide that takes you from being a digital dreamer to a physical creator. We are going to walk through the exact step-by-step pre-flight checklist that professionals use to ensure their digital file becomes a perfect physical object, saving you a small fortune in failed prints and a massive amount of frustration. We're going to demystify the jargon and give you the simple, actionable tools to diagnose and fix your models before you ever spend a dime. By the end of this, you won't just know how to prepare a file. You'll understand why it works, turning you from a hobbyist into a pro. So let's start with the single biggest reason for failure, the #1 assassin of 3D prints: creating a model that isn't watertight. Imagine your 3D model is a balloon. To print it, the slicing software, the computer program that tells the 3D printer what to do, needs to know with absolute certainty what is the inside of the balloon and what is the outside. If the balloon is perfectly sealed, it's easy. The air is inside, the world is outside. The slicer can then intelligently slice it into hundreds or thousands of layers and tell the printer exactly where to place the material. But what if your balloon has a tiny microscopic hole in it? What happens? The air leaks out. The distinction between inside and outside is gone. The entire concept of the balloon collapses. This is precisely what happens with your 3D model. If there is even a single tiny hole in the mesh, the software panics. It can't determine what's inside and what's outside. This state is called non-manifold geometry, which is just a fancy $20 term for leaky. The software tries its best to guess, but its guesses are often catastrophic, leading to missing walls, bizarre internal structures, or just that stringy spaghetti mess we all dread. Your file must be a single, continuous, sealed surface with no holes. It has to be completely watertight. This problem shows up in a few different ways. The most obvious is just a literal hole in your model. Maybe you were moving some vertices around and accidentally deleted a face, leaving a gap. On a complex model, this can be nearly impossible to spot with the naked eye. But a computer will find it instantly. Another, more sinister version of this problem is internal geometry. Let's say you're designing a coffee mug. You model the outside shape, then you model the inside shape as a separate piece and just push it into the first one. On your screen it looks perfect. But to the printing software, you've just created chaos. You have two different surfaces occupying the same space, and the software has no idea which one is the real surface. Do I print the outside? The inside? Both? It's like giving a builder two different blueprints for the same wall, and telling him to figure it out. The result is confusion and failure. Your model must be one single, unified shell. And then there's the weirdest one of all, flipped normals. Every tiny triangle or polygon that makes up your model has a direction. It has an outside and an inside. This direction is called its normal. Think of it like this. Every panel on the outside of a car is facing outwards. But if a mechanic accidentally installed one door panel inside out, with the metal facing in and the upholstery facing the rain, it would be instantly wrong. That's a flipped normal. When a few triangles on your model are facing the wrong way, you're telling the printer that part of the object is inside out. The printer software sees this, gets hopelessly confused about where the solid part of your model is supposed to be, and generates a flawed print path. So, you've got holes, you've got internal faces, and you've got flipped normals. The three horsemen of the print apocalypse. How on earth do you find and fix these invisible errors? You don't need to hunt for them manually, triangle by triangle. That would be insane. Instead, we use specialized software, and the best part is many of the best tools are completely free. Programs like Mesh Mixer, or even the built-in 3D print toolbox in Blender, are your new best friends. They are like an MRI for your 3D files. You simply import your model, your STL or OBJ file, and you click a single button, usually called something like Inspector or Analyze. The software then does a full diagnostic scan of your entire model's geometry. It's not looking at how pretty it is. It's looking at the mathematical integrity of the surface. And then, like magic, it highlights all the problems. It will put bright blue or red markers on every single non-manifold edge. It will show you exactly where the holes are. It will point out any surfaces that are fighting with each other. Takes all the guesswork out of the equation. You can see instantly that your balloon is leaky. Now for the even better part. Most of these programs have an auto repair function. You click the button, and the software does its absolute best to intelligently patch the holes, delete the internal garbage geometry, and unify the entire mesh into a single, clean, watertight shell. In a huge number of cases, a single click can take a file that was destined for the trash can and make it perfectly printable. It is one of the most satisfying clicks in all of 3D modeling. But, and this is a very important but, it's not a magic wand. Sometimes the automatic repair can create weird results, especially on very complex or badly damaged models. It might patch a hole in a way that slightly changes the shape you intended. That's why it's critical to understand what it's doing. By diagnosing the file first, you can see the problem areas, try the auto repair, and then inspect its work to make sure the result is still your original vision. So, you've run the analysis. You've patched the holes. Your model is now a mathematically perfect, sealed, watertight object. You're ready to upload it and print, right? You're finally safe? Not even close. Because you could have a perfectly sealed model that is as thin as a single sheet of paper. And the moment the printing services machine tries to build that paper-thin wall with molten plastic or laser-fused powder, it will instantly disintegrate, crack, or warp into nothing. You've solved the leakiness, but you haven't solved for the laws of physics. The next colossal mistake that ruins countless prints is ignoring wall thickness, and that is the giant we are going to conquer next. Imagine you've just spent 50 hours sculpting the perfect miniature for your tabletop game. A heroic knight, clad in impossibly intricate armor, his sword raised in defiance. Every link in his chainmail, every filigree on his helmet, is a work of art. You upload the file, your heart pounding with excitement. You choose a high-detail resin material, pay the premium, and wait. A week later, a small box arrives. You open it with the reverence of an archaeologist unearthing a relic. And inside is dust, and a few larger chunks that look like shrapnel. The glorious sword is a broken toothpick. The shield is a sad, warped crescent. The knight himself has crumbled into a pile of gray despair. What happened? Your model was a ghost. It existed on your screen as a beautiful illusion, but in the real world, it lacked the substance to hold itself together. This is the brutal lesson of wall thickness. It is, without a doubt, the #1 reason beautiful designs become tragic failures. It's the difference between a durable, functional object and a pile of expensive, heartbreaking rubble. So let's demystify it. Wall thickness is simply the distance between one surface of your model and its opposite, inner surface. If you have a model of a coffee cup, the wall thickness is how thick the ceramic is. Too thin, and it's a fragile eggshell. Too thick, and it's an unwieldy brick that costs a fortune to print. It's the literal substance of your creation. Why does this one setting hold so much power? Because every single 3D printing technology has a physical limit. It's not a suggestion, it's a law. Let's break down the big three. First, you have the most common type of printing, the kind you see on desktops, called fused deposition modeling, or FDM. This is the one that lays down melted plastic layer by layer, like a super precise hot glue gun. That glue gun has a nozzle, a physical metal tip with a hole in it. A common size is 0.4 millimeters. Now imagine you designed a wall that's only 0.2 millimeters thick. The printer literally cannot create it. It's like trying to paint a pinstripe with a fire hose. The software will try, but the result will be a pathetic, stringy mess, or more likely nothing at all. The printer will just skip it, leaving a gaping hole in your model. Next up is resin printing technologies like SLA or DLP. These are the champs of high detail. Using UV light to cure liquid resin layer by microscopic layer, they can produce incredibly fine features, way thinner than an FDM printer. So you're safe, right? Wrong. While a resin printer might be able to form a paper-thin wall, that wall is now suspended in a vat of liquid. After the print is done, it has to be washed in alcohol, blasted with compressed air, and cured under a powerful UV lamp. Your delicate, wafer-thin wall, which looks so good on screen, will fold, warp, or snap clean off during this violent post-processing stage. It's like a beautiful butterfly wing trying to survive a car wash. It just won't. Finally, there's the industrial powerhouse, selective laser sintering, or SLS. This technology uses a high-powered laser to fuse together particles of powder, like nylon or metal. A huge advantage of SLS is that the unfused powder around the object acts as a support structure, so you don't need to add those little tree-like supports. But that doesn't give you a free pass on wall thickness. After the print is done, your model is a solid object buried in a cake of fine powder. It has to be excavated, often using brushes and compressed air. If your walls are too thin, they are now impossibly fragile. Imagine trying to unearth a fossil made of meringue. The force of the air and the brushing will simply sandblast your delicate features into oblivion, or snap them right off. So what's the magic number? How thick is thick enough? This is where so many people get paralyzed. They either make everything paper thin to save money, or they make it a solid block out of fear. The answer is the Goldilocks zone. Not too thin, not too thick. Here's the most important piece of advice in this entire section. Every single online 3D printing service has a document on their website called Design Guidelines. It might be called Material Specs or Technical Information. Find it, read it, memorize it. This document is your Bible. It will tell you the exact minimum wall thickness for every single material they offer. But to give you a solid rule of thumb, a safe starting point for most standard non-flexible plastics like PLA, ABS, or nylon is about 1.5 to 2 millimeters. For parts that need to be strong, that need to clip together or bear a load, you should be aiming for 3 millimeters or more. For high-detail resins, you might get away with as little as 0.8 to 1 millimeter for decorative features, but again, check the guidelines. These aren't suggestions. They are the physical constraints of the machine and the material. Ignoring them is like arguing with gravity. You will lose. Okay, so how do you actually check this in your software before you waste $100? Thankfully, it's easier than you think. Most 3D modeling programs have built-in tools for this exact purpose. If you're using Blender, a fantastic free program, there's a built-in add-on called the 3D Print Toolbox. You just have to enable it. It has a button that says Thickness. You type in the minimum thickness from your service's design guide, say 1.5 millimeters, and you hit the button. It will analyze your model and highlight every single area that's too thin, usually in bright red. It's a digital X-ray that shows you every single point of failure before it happens. If you're using a CAD program like Fusion 360 or SolidWorks, you're often in a better position because you're building with precise dimensions from the start. But a killer feature in these programs is the section analysis tool. This lets you create a digital cross-section, slicing your model in half virtually so you can see inside. You can drag this cutting plane through your entire model and visually inspect every single wall to make sure it looks robust. A powerful free tool that everyone should know about is Mesh Mixer. You can import your model and use its thickness analysis. This tool is brilliant. It creates a color heat map of your entire object, showing you the thinnest parts in red and the thickest parts in blue. You can see at a glance where your problem spots are. Now, what if you find a problem? What if your beautiful nightscape is a sea of red, indicating it's only 0.3 millimeters thick? The fix is often a single click away. Most programs have a function called solidify or shell. What this does is take your single layer surface and gives it a uniform thickness. You just tell it, make this 2 millimeters thick, and boom, it extrudes the entire surface inward or outward, instantly creating a strong, printable wall. It's like magic. For more complex issues, you might have to go in and manually sculpt or pull the surfaces to thicken them up. But for 90% of problems, a solidify modifier is your best friend. Let me tell you a quick story about my friend Mark. Mark was designing a custom case for a Raspberry Pi project. He spent weeks on it in a surface modeling program, making it look incredibly sleek and futuristic, all flowing curves and sharp vents. It looked like something out of a sci-fi movie. He uploaded it to an SLS service to be printed in tough nylon. The quote was high, but he figured it was worth it for his masterpiece. When the part arrived, it was a disaster. The sleek vents, which looked so cool on screen, were so thin they had warped from the heat of the laser. The snap-fit clips he designed to hold the case together were as thin as a credit card and broke the instant he tried to close it. The entire thing was a flimsy, useless piece of plastic. Mark had made two critical errors. He designed the object based on how it looked, not on how it would be made. And he never once looked at the design guidelines for the nylon material he chose. A 5-minute check with a thickness analysis tool would have shown him that his entire design was a ticking time bomb. He had to go back, thicken every single wall, reinforce the clips, and simplify the vents. The second print worked perfectly. But that first failed print? It was a very expensive lesson in the unforgiving reality of wall thickness. You have to think like a sculptor and an engineer at the same time. Your model isn't just a collection of pretty pixels. It's a blueprint for a real physical object that has to survive being created, cleaned, and shipped to your doorstep. Respecting wall thickness is the single most important step in ensuring your digital dream doesn't become a physical nightmare. So you've done it. Your model is now a fortress. It's watertight, and its walls are thick and strong. You are ready. You upload your file, confident in its structural integrity. You click Get Quote, and your jaw hits the floor. The price is astronomical, 3 or 4 times what you budgeted for. Or maybe the site gives you a bizarre error message. Model exceeds maximum printable dimensions, even though it looks small on your screen. What's going on? You've just slammed headfirst into the next great filter that separates beginners from pros. The treacherous and often confusing world of scale and units. And mastering that is exactly where we are going next. It's a digital lost in translation moment. Your 3D software is speaking one language of size, and the printing services uploader is listening in another. The result? Chaos. A beautiful 6-foot-tall suit of armor you designed becomes a miniature for a dollhouse. A delicate 2-inch pendant becomes a massive, unprintable monstrosity, the size of a manhole cover. This isn't a bug. It's a fundamental misunderstanding of how digital objects relate to the physical world. Here's the secret that no one tells you when you start. 3D models in their purest form have no size. They are just a collection of points, called vertices, floating in an imaginary digital space. The distance between 2 points might be 10, but 10 what? 10 inches? 10 millimeters? 10 miles? Your design software often doesn't care. To it, it's just the number 10. This abstract concept is powerful for artists, letting them create without being bogged down by physical constraints. But for us, for people who want to turn those digital dreams into physical reality, this ambiguity is a trap. When you upload that file, the printing services software has to make a choice. It has to decide what that 10 means. And 9 times out of 10, it's going to assume you meant millimeters. This brings us to the Great Divide. The metric system versus the imperial system. Here in the United States, we're used to thinking in inches and feet. It's how we measure everything from a piece of paper to a football field. But the world of 3D printing, from the hardware to the software to the community, overwhelmingly speaks metric. Specifically, it speaks in millimeters. Millimeters are the universal language of additive manufacturing. They are small enough to provide incredible precision for the tiny details that make a print great. And they are a simple base 10 unit that makes scaling and math a breeze. So, the first and most important piece of advice I can give you is this: learn to think in millimeters. Even if you have to keep a converter tab open in your browser, start internalizing it. A US quarter is about 24 millimeters in diameter. An inch is 25.4 millimeters. A standard credit card is about 85 millimeters long. When you start your project, your first thought shouldn't be, I want this to be 5 inches tall. It should be, I want this to be 127 millimeters tall. Embracing the millimeter is the first step to eliminating scale problems forever. Okay, so how do we put this into practice? It all starts inside your design software, before you even create a single polygon. Let's walk through the process. First, you need to tell your software what you're doing. Buried in the settings or preferences of almost every 3D program, whether it's Blender, Fusion 360, ZBrush, or Maya, is a section for scene properties or units. This is your command center for scale. Find it. Your mission is to set 2 things. First, set the unit system to metric. Second, set the length or unit of measure to millimeters. By doing this, you are creating a contract with your software. You're saying, from now on, when I type the number 1, I mean 1 millimeter. Not 1 meter. Not 1 inch. 1 millimeter. This simple act aligns your virtual world with the real world of the 3D printer. Now, the tools inside your software become infinitely more useful. The measurement tool, the ruler, the dimension guides, they all now speak the language of your final product. This leads to the second crucial habit: model to real-world scale from the very beginning. Don't just eyeball it. Don't just sculpt something that looks about right on your screen and assume you can just scale it later. That's a recipe for disaster. You wouldn't build a house without a blueprint, and you shouldn't build a 3D model without a sense of its final physical dimensions. If you're designing a custom phone case, get a real phone and a set of digital calipers. Measure its exact length, width, and thickness in millimeters. Input those dimensions into your software. Create a simple block of that exact size to serve as your guide. Now build your case around it. If you're designing a miniature figure for a tabletop game, decide if it's a 28mm scale or a 32mm scale. Use a reference model of that size right in your scene. This practice not only prevents scaling errors, but it also makes you a better designer. It forces you to consider the real-world implications of your design choices. Will this wall be too thin to print? Is this hole big enough for a screw to pass through? You can only answer these questions if you're working with accurate, real-world numbers from the start. Now let's say you've done everything right. You set your scene to millimeters. You meticulously modeled your object to the exact size you want. You are ready to export. You hit export as STL, and you're presented with a pop-up window full of checkboxes and number fields. This is the final gatekeeper, and it's where so many people stumble. In this export dialog, you need to look for two things. The first is a scale setting. If you have set up your scene units and modeled to scale correctly, this number should almost always be 1.0. Setting it to 1.0 means export it exactly as it is. Don't change it unless you have a very specific reason and you know exactly what you're doing. The second, and arguably more important, setting is a little checkbox that might say apply modifiers, or more critically, apply transform or apply scale. You must check this box. Let me explain why. Sometimes in 3D software, you can scale an object visually without actually changing its base data. It's like putting a magnifying glass over it. It looks bigger, but the software still remembers its original, smaller size. Ticking that Apply Transform box forces the software to bake in that new size. It makes the visual size the actual size. Forgetting this step is one of the most common reasons why a perfectly scaled model in your software suddenly imports incorrectly into the printing service. But what if it's too late? What if you already have a model that you downloaded, or one you made before you knew any of this and it's the wrong scale? Don't worry, you don't have to start over. The best solution is to fix it in your 3D software. Let's say you designed a part that is 4 units tall, and you were thinking in inches. You upload it, and the service reads it as 4 millimeters, which is tiny. The fix is simple math. There are 25.4 millimeters in an inch. So, you go back into your software, select your object, and scale it up by a factor of 25.4. Your 4-unit object is now a 101.6 unit object. Now apply that transform, export it with a scale of 1.0, and when you upload it, the service will read it as 101.6 millimeters, which is exactly 4 inches. Problem solved. However, many online printing services know this is a common problem, so they've built in a life raft. When you upload your model, you'll often see input boxes showing the model's dimensions. If your model uploads and says it's 4 millimeters wide, but you know it should be 4 inches, you can often just type 4 in the box and change the unit drop-down next to it from mm to in. The website will do the conversion for you and automatically scale your model to the correct size. This is a fantastic quick fix. But be warned, it only fixes the model for that specific order. The original file on your computer is still the wrong size. Best practice is always to fix the source file. Finally, after you upload your file, pay close attention to the information the website gives you. It will almost always show you what it thinks the final dimensions are. This is your final sanity check. It will display something called the bounding box, an imaginary cube that perfectly contains your entire object, and lists its dimensions in X, Y, and Z. Look at those numbers. Do they make sense? You wanted a coffee mug. Are the dimensions roughly 95 millimeters tall and 80 millimeters wide? You wanted a keychain. Is it in the ballpark of 50 millimeters by 30 millimeters? If the numbers look wildly off, you know you have a scale issue and you need to go back and fix it before you click Order. You've done it. You navigated the treacherous world of units and scale. You've set up your software, modeled with precision, and exported with confidence. Your file is uploaded and the dimensions on the screen are perfect. You breathe a sigh of relief. You've conquered the second great filter. You're ready to print. But then just as you're about to add it to your cart, you see a new error message pop up. It's a single terrifying technical-sounding word. Warning: your model is not manifold. What on earth does that mean? It sounds like a problem with the Starship's engine, not a 3D file. This error means your model has holes. It isn't watertight. And just like you can't fill a leaky bucket with water, a 3D printer can't fill a leaky model with plastic. Sealing these digital holes and making your model perfectly solid is the next, and perhaps most critical skill you need to master. And that is exactly where we're headed. So what actually happens when you send a leaky model to a printer? It's not just that it fails. It's how it fails that's so maddening. The software that slices your model into layers, called a slicer, gets profoundly confused. It sees a hole and it doesn't know what's inside versus what's outside. It's like giving someone a map with a giant chunk missing. They can see the destination and they can see where they are, but the path between them is a void of pure chaos. The slicer might try to print paper-thin walls where there should be solid infill. It might create bizarre, stringy structures inside your model, trying desperately to bridge a gap that was never meant to be there. Or, in many cases, it will just give up entirely, throwing an error message that leaves you scratching your head. Your beautiful design becomes a digital ghost, impossible to bring into the physical world. To prevent this, you need to become a digital detective, hunting down 4 specific culprits that create these leaks. Think of them as the 4 horsemen of print failure. The first and most obvious culprit is a literal hole, a missing face. This happens all the time, especially when you're combining different shapes or modifying an existing model. You might delete a section, and the software doesn't automatically patch the opening. It's a gaping wound in your model's geometry. To the computer, this isn't just an opening. It's a breakdown in logic. The very definition of a solid object is a continuous closed surface. A hole breaks that definition. The second culprit is more insidious: internal faces. These are walls, surfaces, and bits of geometry hidden inside your supposedly solid model. Imagine you're building a 3D model of a simple house. Now imagine you accidentally build a wall that runs right through the middle of the living room, completely sealed off with no doors. You can't see it from the outside, but the slicer software can, and it gets confused. It asks, is this wall supposed to be here? Is the living room now 2 separate smaller rooms? Which side of this internal wall is the real inside? This ambiguity can cause the printer to create strange voids or solid sections where they shouldn't be, weakening the final print or causing it to fail entirely. These are digital tumors and they need to be surgically removed. The third horseman is the trickiest to understand, but it's responsible for some of the most baffling print failures. It's called a flipped normal. Now stay with me here. Every single flat surface or face on your 3D model has a direction. It has an outside and an inside. This direction is called its normal. Think of it like a tiny arrow pointing perpendicularly away from the surface. For a solid object, all of these arrows should be pointing outwards, away from the center of the model. A flipped normal is when one or more of these faces gets turned around so its arrow is pointing inwards. The best analogy is a t-shirt. When you wear it normally, the outside is facing out. But if you put it on inside out, the seams and tags are showing. The fabric is still there, the shape is the same, but its surface is fundamentally facing the wrong way. When a slicer sees a flipped normal, it thinks that part of your model's skin is inside out. It interprets that area as a hole, a void, a negative space, even though the geometry is perfectly connected. This can lead to entire sections of your model simply vanishing from the final print, as if they were never there. And the fourth and final culprit is the zero-thickness wall, also known as a 2D surface. This is a wall that is infinitely thin. It's a plane that has area but no volume. In the digital world, you can create a surface made of a single face. But in the real world, you can't build a wall out of something with no thickness. You can't 3D print a sheet of paper that is literally 1 atom thick. Your printer nozzle has a specific diameter. It lays down a bead of plastic with a real physical thickness. When the slicer sees a zero-thickness wall, it has no instructions on how to build it. Can't make it exist. So, it usually just ignores it completely, leaving a gap in your model that becomes a catastrophic failure on the print bed. So, how do you find and exterminate these 4 horsemen? Your first line of defense is often a single magical button. Most 3D modeling and repair software like the free programs Meshmixer or Blender have an automated repair tool. It might be called Make Solid, Auto Repair, or Watertight. When you click this button, the software analyzes your entire model. It aggressively hunts for holes and tries to patch them. It looks for those rogue internal faces and deletes them. It tries to unify all the normals so they're all pointing outwards. It's an incredibly powerful first step. For simple models with minor issues, one click can often solve everything. But, and this is a big but, it's not foolproof. Automated tools are making educated guesses. Sometimes, when patching a complex hole, the software might create a weird, ugly surface that doesn't match your design intent. Sometimes, in its quest to delete internal geometry, it might delete something important. It's like using your phone's autocorrect. 90% of the time, it's a lifesaver. But that other 10% of the time, it changes your perfectly reasonable sentence into something bizarre and nonsensical. You should always run the auto repair first. But you must always inspect its work afterwards. This is where you graduate from a button pusher to a true digital craftsperson. You need to learn how to manually inspect your model. Software like Blender has powerful analysis tools built right in. You can enable a feature called Mesh Analysis that paints your model in different colors to reveal problems. It can highlight zero-thickness walls in red, or sharp, unprintable edges in blue. It's like putting on a pair of X-ray goggles that let you see the hidden flaws in your geometry. The most powerful tool in your arsenal is often called Select Non-Manifold. When you run this command, the software automatically highlights every edge that's part of a leak. The edges of any holes will light up like a neon sign. Any faces that are connected improperly will be flagged. This command doesn't fix anything, but it does something even more important. It gives you a precise, undeniable map of every single problem in your model. It's the diagnostic tool that tells you exactly where the digital surgery needs to happen. So, you've run the analysis and you've found the problems. Now it's time to get out the digital scalpel. Let's say the analysis tool has highlighted the edges of a simple circular hole. In most programs, you can simply select that entire loop of edges and hit a Fill or Make Face command. The software will stretch a new piece of digital skin over the opening, healing it instantly. For more complex, jagged holes, you may need to do more delicate work, selecting two edges on opposite sides of the hole, and using a bridge tool to create a new face between them, slowly rebuilding the surface one piece at a time. What about those inside-out faces, the flipped normals? Your software will also have a way to visualize these. Often, it's a setting that displays the direction of the normals as little lines or by coloring the front and back of a face in different shades. When you spot a section that's the wrong color, the fix is usually astonishingly simple. You select the offending faces and use a Flip Normals command. Or even better, you can often select the entire model and click Recalculate Outside. The software will look at the overall shape and make a very good guess about which side is supposed to be the exterior, flipping all the normals to point the correct way in one go. Fixing internal geometry is the most hands-on repair. You have to navigate your camera inside the model, like you're piloting a tiny submarine. Once inside, you can see the extra walls and floating bits of digital debris. From there, it's a simple, satisfying process of selecting those unwanted faces and deleting them, cleaning out the inside of your model until it's perfectly hollow and uncluttered. By learning these techniques, running the auto repair, analyzing the results, and then manually fixing the holes, flipping the normals, and deleting the internal junk, you transform your model. It goes from being a fragile, leaky suggestion of a shape into a perfectly sealed, unambiguous, solid object. It is now a watertight vessel, ready for the slicer to understand it perfectly. Every single layer will be clear. Every instruction to the printer will be precise. You've closed all the leaks. But now that your bucket is perfectly sealed, a new critical question arises. The bucket can hold water, but is it strong enough? If the walls of that bucket are only as thick as a sheet of paper, it will collapse the moment you try to fill it. Your 3D model is the same. It may be solid, but if its walls are too thin, it will crumble into dust during printing or break in your hands. Mastering wall thickness is the next crucial step from making a model possible to print, to making it practical and strong. Mastering wall thickness is the next crucial step from making a model possible to print, to making it practical and strong. Think of it like this. You can build a house out of solid concrete walls. It'll be strong, sure, but it will also be insanely expensive and heavy. Or you could build it with walls made of paper. It'll be cheap, but the first gust of wind will knock it over. The architect's job is to find that perfect balance. Walls thick enough to support the roof and withstand the elements, but not so thick that they're wasteful or impractical. You are now that architect for your 3D model. Every 3D printing technology has a physical limit, a point where a feature is just too thin to exist in the real world. For a standard desktop FDM printer, the kind that lays down melted plastic like a tiny hot glue gun. A thin wall is like trying to draw a line with a single wobbly strand of hot spaghetti. It will sag, it will be weak, and it might not even stick to the layer below it. For resin printers, which use UV light to cure liquid plastic, the problem is different but just as real. As the print builds, the model is pulled out of the resin vat. If a wall is too thin, that suction force can literally rip it apart or warp it like a wet piece of cardboard. Even if it survives the print, a paper-thin wall is too fragile to withstand the mandatory post-processing steps of being washed in alcohol and blasted with more UV light to fully cure. And for the industrial powder-based systems used by most online services, like SLS, where a laser fuses together grains of nylon powder, a thin wall is like the edge of a sandcastle. The laser might not be able to fuse enough powder together to create a solid structure, leaving you with a fragile, crumbly edge that can disintegrate during the depowdering process. Online services know this. They have seen thousands of models fail. That's why they establish a minimum wall thickness. It's not an arbitrary rule. It's a law of physics for their specific machines and materials. They are protecting you from receiving a box of expensive plastic dust. So what is this magic number? Where is the Goldilocks zone? The frustrating but honest answer is, it depends. It depends entirely on the material you choose, the printing technology, and the overall size and geometry of your model. But don't worry, there's a simple process to find it. First, a general rule of thumb. For most strong, functional parts printed in common plastics like nylon or PLA, a wall thickness of 1 to 2 millimeters is a fantastic, safe starting point. That's about the thickness of a US quarter. If you design most of your model with walls at least this thick, you'll avoid the most common failures. But most isn't all. To get it right, you have to do a tiny bit of research on the service's website. This is the single most important habit to develop. Let's walk through it. Go to any online 3D printing service. Find their materials page. Click on the material you're interested in. Let's say it's called versatile plastic or P12 nylon, which are very common. On that materials page, there will be a link or a tab that says Design Guidelines or Technical Specifications. Click it. This page is your Bible. It will list, clear as day, the minimum wall thickness, and it's often a number like 0.7 millimeters or 1 millimeter. This is the absolute thinnest your model's walls can be. Your mission is to find any part of your model that violates this rule. Ignoring this number is the fast track to disappointment. Imagine you've spent 40 hours designing a beautiful, intricate statuette of a knight. The armor plates are detailed, the cape is flowing, and the sword is raised high. You upload it, you pay for it, you wait a week, and the box arrives. You open it, and the sword is snapped off at the hilt. The edge of the cape has crumbled away. Why? Because while the main body was thick and strong, you modeled that sword to be a realistic, razor-thin 0.2 millimeters. The printing process couldn't handle it, or the person packing it breathed on it too hard. A heartbreaking but completely avoidable failure. Now you might be thinking, okay, I'll just make everything super thick. I'll make the walls 10 millimeters thick just to be safe. You can do that, but you're creating a new set of problems. The first is cost. Most 3D printing services calculate price based on the volume of material used. A model with walls that are twice as thick doesn't just cost twice as much. Depending on the geometry, it could cost 4 or even 8 times more. That $30 miniature suddenly becomes a $200 paperweight. The second problem is physics. With certain materials and large, flat surfaces, overly thick walls can introduce immense internal stress as the part cools down from its printing temperature. This stress can cause the part to warp, curl up at the edges, and ruin its dimensional accuracy. It's like a thick wooden board twisting as it dries. You've made it so strong that it tears itself apart. The goal is not maximum thickness, it's optimal thickness. So how do you check your model? You don't have to get out a digital ruler and measure every single surface. Your 3D software has tools for this. In programs like Blender, Fusion 360, or SolidWorks, there is almost always a wall thickness analysis tool. It's like putting on a pair of X-ray goggles for your model. You typically tell the tool the minimum value you found on the service's website, let's say 1 millimeter. Then you click Analyze. The software will instantly color code your entire model. Areas that are safely above the minimum will show up as green. Areas that are getting dangerously close might show up as yellow or orange. And the critical problem areas, the walls that are thinner than your 1 millimeter rule, will be highlighted in bright red. There it is. No guesswork. Your software is now pointing a giant red arrow at every single part of your model that is destined to fail. Your job is now simple. Go into those red zones and thicken them up. Maybe you need to add a bit of material to the back of that flowing cape. Maybe you need to make that sword blade just a little less realistic and a little more robust. You make the changes, you run the analysis again, and you keep going until all the red is gone. As you get more comfortable, you'll start to understand some of the nuances. For example, there's a difference between a supported wall and an unsupported wall. A tall, thin wall standing all by itself is an unsupported wall. It's incredibly weak, like a single fence post in a storm. But if you take that same thin wall and connect it to other walls, maybe as part of a grid or a honeycomb pattern, it becomes a supported wall. It borrows strength from its neighbors. You can often get away with slightly thinner walls if they are well supported by the surrounding geometry. You'll also learn to distinguish between structural thickness and surface detail. The main wall of a box needs to be structurally sound, say 2 millimeters thick. But text you engrave into that wall can be much finer. The service's design guide will often list a separate, smaller value for minimum detail size, or embossed/engraved details, which might be as low as 0.2 or 0.3 millimeters. This is because those details aren't holding anything up. They are fully supported by the thick wall they're attached to. Understanding this difference allows you to create highly detailed models that are still incredibly strong. By checking the design guides and using your software's analysis tools, you transform wall thickness from a mysterious source of failure into a simple, solvable engineering problem. You are taking control of the design and ensuring that the object you hold in your hands will be every bit as strong and perfect as the one you imagined in your mind. So now you have a model that's a single, solid, watertight mesh with strong, robust walls. It's printable. It's durable. But you upload it to the service and the price quote comes back. And it's $100 for a model the size of your fist. Why? Because it's a solid chunk of plastic. The secret to slashing that cost, sometimes by over 80 or 90%, without sacrificing strength, lies in a technique called hollowing and shelling. And that's where we're going next. Imagine you're at the grocery store, and you see two giant chocolate Easter bunnies. They look identical. Same size, same shape, same beautiful glossy finish. But one costs $5 and the other costs $50. You pick them up. The $5 one is light as a feather. The $50 one is a brick. It's solid chocolate. Now which one are you buying? Unless you're planning to use it as a doorstop, you're buying the hollow one. You still get the experience, the shape, the fun, but at a fraction of the cost and weight. This is the single most important money-saving concept in 3D printing, and almost every beginner gets it wrong. They design a beautiful solid model, upload it, get a quote for $200, and abandon their project forever. They were trying to print the solid chocolate bunny. Hollowing or shelling is the digital equivalent of making that hollow Easter bunny. We take our solid model and we scoop out the inside, leaving a thin, uniform wall like an eggshell. The immediate, obvious benefit is cost. You're no longer paying for all that internal, unseen material. For many technologies like SLS or multi-jet fusion, the price is directly tied to the volume of your model. By hollowing it, you can slash that volume and therefore the price by 80, 90, sometimes even 95%. It is the difference between an idea being a fun thought experiment and it becoming a real object you can hold in your hands. But the benefits go way beyond just your wallet. It's also about physical reality. A solid object is heavy. If you're designing a part for a drone, a piece of cosplay armor, or anything that needs to be lightweight, hollowing is non-negotiable. You get the same external dimensions, the same look, but a fraction of the weight. And here's the reason that trips up even intermediate users, especially in the world of resin printing. Hollowing is crucial for the success of the print itself. Imagine a solid resin part being printed. It's built layer by layer, with each new layer being cured by UV light. When you print a large solid cross-section, two bad things happen. First, you generate a ton of heat from the chemical reaction of the resin curing. This internal stress can cause cracks and warping days or even weeks after the print is finished. Second, and more dramatically, you create a massive suction force. As the build plate pulls up to create the next layer, it's trying to pull this wide, flat, cured layer out of the vat of liquid resin. The suction can be so strong it literally rips the part off the build plate or separates the layers mid-print, resulting in a catastrophic failure. Hollowing dramatically reduces that cross-sectional area. Instead of a solid disc, you're just printing a thin ring. The suction forces drop to almost nothing. The internal stresses disappear. The print survives. So hollowing isn't just a cost-saving trick, It's a professional technique for ensuring quality and success. Okay, so you're sold. You open your software, you find the hollow button, you click it, and you've just created a digital time bomb. Because you missed the most critical step. You've created a sealed container. A beautiful eggshell with no way in or out. If you send this to a powder-based service like SLS, all the loose, unsintered powder that gives the model its shape during printing will be trapped inside forever. You'll have a model that's supposed to be light, but it's full of powder, rattling around like a maraca. You can never get it out. But if you send this sealed file for a resin print, the consequences are far worse. The inside of your model will be filled with uncured, liquid resin. It's trapped. The service will wash the outside, but the inside remains a toxic liquid slush. Over time, that resin will find a way out. It will seep through microscopic pores in the print wall, making the surface sticky and dangerous to handle. Worse, gases can build up inside from the slow curing of this trapped resin, and the pressure can literally crack your model open from the inside out days or weeks later. It's a messy, toxic, and heartbreaking failure. This is the #1 mistake I see. But the solution is incredibly simple. Escape holes, or sometimes called drain holes. You must punch at least 2 holes in your hollow model. Why 2? Think about trying to pour soda out of a can with only 1 hole poked in it. It glugs and sputters because air can't get in to replace the liquid coming out. You need 1 hole for the material, be it trapped powder or liquid resin, to escape, and a second hole for air to get in and allow a smooth, easy flow. So where do you put these holes? In the least conspicuous place possible. On the bottom of a base, on a surface that will be glued to another part, somewhere that doesn't ruin the aesthetic of your masterpiece. The size of the holes is also critical. Too small and thick resin won't be able to drain out or powder will get clogged. Check the design guide for the 3D printing service you're using. They will tell you their recommended minimum diameter for drain holes for each material. Don't guess. They know their machines and materials better than anyone. They might say you need 2 5mm holes for this resin, or 2 10mm holes for that material. Follow their guidance. It will save you from failure. Now the next big question is, how thick should the walls be? This is the Goldilocks decision. Too thin and your model becomes incredibly fragile like a real eggshell. It might break during shipping, or even during post-processing at the facility. Too thick and you start to lose the cost and weight savings you were trying to achieve in the first place. You're back to printing a solid chocolate bunny. The right wall thickness depends entirely on 2 things: the size of your model and the material you're printing with. A small 2-inch figurine made from a strong nylon might only need a wall thickness of 1 mm. But a large foot-tall sculpture made from a more brittle resin might need a 3 or even 4 mm wall to support its own weight without warping. Again, the cheat code here is the design guide from your printing service. They have tested the limits of their materials. They will provide a minimum recommended wall thickness for each one. This is your starting point. My personal rule of thumb is to take their absolute minimum and add 0.5 mm or a full millimeter for safety, especially for larger parts. For example, if the guide says the minimum wall thickness for their PA12 nylon is 0.8 mm, I'll design my part with a 1.5 mm wall. It adds a tiny bit to the cost but provides a huge amount of extra strength and peace of mind. It's the cheap insurance that guarantees my part survives the journey. So we've hollowed our model to save cost. We've added escape holes to prevent a disaster. We've chosen a smart wall thickness to balance strength and price. We're already ahead of 90% of beginners. But we can take it one step further. What if you have a large model where even a thick wall might not be strong enough? What if you need the lightness of a hollow part but the rigidity of a solid one? The answer is to think like an architect or an engineer. You don't make a solid wall. You reinforce it from the inside. Most advanced 3D modeling software allows you to add an internal lattice structure or a honeycomb infill inside your hollow model. Think of it like the rebar in concrete or the wooden trusses inside a wall. This internal scaffolding uses a tiny amount of material, but provides immense structural rigidity across the entire part. It prevents the large, flat walls of your hollow model from warping or buckling. You get the best of both worlds. The massive cost and weight savings of a hollow part, combined with the strength and stability that rivals a solid object. This is the pro move. When you upload a file with a well-designed internal lattice, you're signaling that you know what you're doing. So now you understand the secret. It's not about just making a 3D shape. It's about being clever with its internal geometry. You've hollowed it out, you've determined the perfect wall thickness based on the material's datasheet. You've cleverly placed your escape holes on a hidden surface, and maybe you've even added an internal lattice for uncompromising strength. Your file is now lean, efficient, strong, and printable. You've transformed that $200 quote into a $20 reality. You've solved the problem of volume. But as you stare at your beautifully optimized model, there's a silent force waiting to ruin your print, a force that affects every single 3D printing technology: gravity. Your model has areas that stick out, floating in midair with nothing beneath them. These are called overhangs, and if you don't handle them correctly, your print will collapse into a stringy, drooping mess. The art of defying gravity is our next challenge. So, how do we command plastic to hang in the air? We can't. At least not without a little help. Imagine you're building a bridge with Legos. You can't just start building the flat roadway in the middle of the gap. You have to build columns up from the ground first, and then build the road on top of those columns. Once the bridge is complete and self-supporting, you could, in theory, remove the columns. 3D printing works on the exact same principle. The printer is like a tiny robotic hot glue gun, drawing one layer of your model at a time, each one on top of the last. It can handle a little bit of an angle because most of a new layer is still resting on the layer below it. Think of it like a staircase. Each step juts out a little bit, but it's still mostly supported by the solid mass beneath it. This leads us to the most fundamental rule of thumb in 3D printing, the 45-degree rule. Generally, a printer can successfully print overhangs that are at an angle of 45 degrees, or less from the vertical. Anything steeper than that, say a flat 90-degree overhang like the underside of a table or the outstretched arms of a figurine, and you're asking the printer to lay down molten plastic onto thin air. And what happens when you do that? Gravity wins. Every time. The plastic will droop, curl, and turn into a mess that looks like spaghetti. This is where we introduce the unsung hero of complex 3D prints: supports. Supports are temporary structures that the printing software automatically generates. They are, quite literally, the scaffolding for your model. They build up from the print bed, or from another part of the model itself, reaching up to meet the exact point where that critical overhang begins. They create a platform for the printer to build upon, ensuring those floating parts of your model are printed perfectly. Once the entire print is finished and has cooled down, these supports are designed to be broken away, snapped off, and discarded, revealing the perfect complex shape you designed. Now, not all scaffolding is built the same. In the world of 3D printing, you'll primarily encounter two types of support structures, and the choice between them can dramatically affect your final part and your final bill from the printing service. First, you have the traditional standard supports. You might also hear them called linear or accordion supports. These are like pillars or thin walls that go straight down from every single point of an overhang to the build plate. They are the brute force method. They are incredibly stable and reliable, providing a rock-solid foundation for the overhangs above. However, they have downsides. They use a significant amount of material, which increases the cost and print time. And because they often create a dense mesh of plastic, they can be difficult and time-consuming to remove. More importantly, they make contact with your model across the entire surface of the overhang, which can leave behind a rough texture, or what we call scarring, on the final part. Then there's the more elegant solution: tree supports. Instead of dense walls, tree supports look like, well, trees. They start with a few thick trunks at the base, and then branch out into smaller and smaller limbs, reaching up and touching only the most essential points of your overhangs. Think of it as the difference between building a solid brick column and using a carefully designed, organic-looking scaffold. The advantages are huge. Tree supports use significantly less material, which means a lower cost and faster print time. They are often much easier to remove, sometimes snapping off in one clean piece. And because they only touch your model at specific, tiny points, they leave behind much less scarring, resulting in a cleaner surface finish. So why wouldn't you use them every time? Well, generating these complex structures takes more computational power for the slicing software, and for very large, heavy overhangs, they might not provide the same level of rigid stability as their brute force counterparts. So, when you upload your model to an online service, their software is going to analyze it for any angle steeper than that 45-degree threshold. It will then automatically recommend adding supports. You'll often be given a choice between standard and tree-like structures. Understanding this trade-off is key. You're balancing cost, surface finish, and structural integrity during the print. But what if I told you the best support structure is no support structure at all? This is the single biggest trick that separates beginners from experienced users. Before you even think about adding supports, you have to ask yourself one critical question. Can I just turn the model? This is called orientation. The way you position your model on the virtual build plate is one of an online service's biggest single factors in determining your print's success and cost. Let's imagine you're printing a capital letter I. If you print it standing up, the two arms jut out at an angle. They'll likely be just fine right on that 45-degree edge. But now, imagine printing a capital letter T standing up. The horizontal top bar is a massive 90-degree overhang. To print this, you'd need a huge amount of support material underneath both arms, which you'd then have to painstakingly remove, leaving a rough bottom surface on those arms. But what happens if you just take that T and lay it flat on its back? Suddenly, there are zero overhangs. Zero. The entire model can be printed perfectly with no supports needed at all. It will print faster, use less material, be significantly cheaper, and the final part will be stronger and cleaner. By simply rotating the part before you even upload it, you've completely changed the game. This is the strategic thinking you need to apply. Look at your model. Turn it around in your 3D software. Which orientation presents the fewest steep overhangs? Can you sacrifice the surface quality of a less important face by orienting it downwards to avoid supports on a more critical, visible face? For example, if you're printing a small statue, laying it on its back might eliminate the need for supports on the detailed face and arms, but it would create a flat, less detailed surface on the back. Is that a trade-off you're willing to make? Online printing services are smart, but they're not always perfect. Their automated orientation tools aim for a good result, but they don't know which surfaces are most important to you. By taking control of the orientation yourself, you are directly controlling the outcome. You can often reduce your quote from an online service by 10, 20, even 30% or more, just by finding the cleverest way to position your part to minimize or eliminate supports. Remember, every time a support touches your model, it leaves a mark. It's unavoidable. The surface where the support connects will never be as smooth and perfect as the other surfaces of the print. It will be a little rougher, a little less defined. This is the price of defying gravity. So your goal is always to minimize these contact points, to hide them on surfaces that aren't aesthetically important, or to get rid of them entirely through clever orientation. We've now built the scaffolding on the outside to hold our model up during its creation. But what about the inside? If you were to pick up a professionally 3D printed part, you might be surprised by how light it is. That's because it's probably not a solid block of plastic. Printing a solid object is incredibly slow, expensive, and in most cases completely unnecessary. The real secret to creating parts that are both strong and lightweight lies within the model itself, in a hidden, internal geometric world that gives the object its strength and structure. This world is called infill, and that's where we're going next. Imagine for a moment that you're an architect, not of buildings but of objects. You've just designed the perfect outer shell, the beautiful facade of your creation. But if you were to print that object completely solid, a solid block of plastic, you'd be making a massive mistake. It would be incredibly slow to print, ridiculously expensive in material, and far heavier than it needs to be. In most cases, a solid object isn't even stronger. The real secret to creating parts that are both strong and lightweight lies within the model itself, in a hidden, internal geometric world that gives the object its strength and structure. This world is called infill, and that's where we're going next. Infill is the internal support structure of your 3D print. It's the secret skeleton. If you were to slice a 3D printed part in half, you wouldn't see a solid chunk of plastic. Instead, you'd see a pattern, a honeycomb, a grid, a complex web that fills the empty space. This internal lattice is what turns a hollow shell into a functional, robust part. And you, the designer, have almost complete control over it. This is one of the most powerful and often overlooked aspects of preparing a file for printing. When you're dealing with infill, you're essentially balancing a classic engineering triangle: strength, speed, and cost. More infill means more strength, but it also means a longer print time and higher material cost. Less infill is faster and cheaper, but your part might snap under pressure. Your job is to find the sweet spot for your specific project. This control comes down to two key settings: infill percentage and infill pattern. Let's break them down. First, infill percentage. This one is simple to understand. It's the density of that internal structure. 0% infill would mean your object is completely hollow, basically a fragile shell. 100% infill means it's a completely solid object. The magic happens in between. For most decorative objects, Things that will sit on a shelf and just look cool like a figurine or a non-functional prop, you only need about 10 to 20% infill. This provides enough internal support to hold the top layers up and gives the model a decent feel in your hand without wasting a ton of material. Think of it as the bare minimum framing needed to keep the walls of a house from collapsing inward. When you step up to standard functional parts, things like brackets, enclosures for electronics, or simple tools, you'll typically want to be in the 20 to 50% range. This is the workhorse range. It provides a great balance of strength, print time, and cost. A part with 40% infill can be surprisingly tough and handle a good amount of day-to-day stress. Now, what if you're printing something that needs to be truly strong? A part that will be under constant load, like a component for a drone, a C-clamp, or a replacement gear. This is where you push into the 50 to 75% range. At this density, the internal structure becomes a dominant feature of the part, creating a powerful, reinforced object that can withstand significant forces. So what about 100%? When would you ever print a completely solid object? It's rare, but there are cases. For very thin parts where there's barely any room for infill anyway, making it solid can actually be simpler. Or for parts that need maximum thermal conductivity or a very specific weight and density. But for 99% of prints, going fully solid is overkill. A well-designed infill pattern at 75% can often be just as strong, or even stronger, while being lighter and cheaper to produce. This brings us to the second, and arguably more fascinating, part of the equation: infill pattern. The percentage tells you how much material is inside, but the pattern tells you how that material is arranged. And the arrangement is everything. Different patterns provide different properties. Some are designed for speed, some for strength in one direction, and some for incredible uniform strength from any angle. Let's start with the sprinters. Patterns like lines or zigzag are the fastest to print. The printer's nozzle can move in long, straight lines without having to change direction often. This makes them fantastic for early-stage prototypes where you just need to check the size and shape of a part quickly. The trade-off? They're only strong in one direction, perpendicular to the lines. They're weak to forces that run parallel to the printed lines. Next up are the all-rounders, the daily drivers. This is where you find patterns like grid and triangles. Grid is essentially two sets of lines printed at 90 degrees to each other, creating a simple, effective mesh. It offers good strength in 2 dimensions, and is a fantastic default choice for many functional parts. Triangles take this a step further. We all know from basic geometry that the triangle is an incredibly strong and stable shape. An infill made of interlocking triangles provides great strength, and is another excellent go-to for general-purpose printing. But now we get to the heavyweights, the specialized patterns for when you need serious performance. This is where things get really cool. A pattern called cubic, for instance, builds stacked tilted cubes. This creates a structure that's strong in all 3 dimensions. It takes a bit longer to print, but the result is a part that resists being twisted or compressed from multiple angles. And then there's gyroid. Gyroid is a mathematical marvel. It's a 3-dimensional, infinitely continuous surface that looks like something out of a sci-fi movie. It has no straight lines. It's all smooth, flowing curves that create a wave-like internal structure. The reason it's so amazing is that it provides nearly uniform strength in every single direction. It doesn't matter if you push, pull, or twist the part. The gyroid infill resists the force almost equally. It's also fantastic at absorbing impacts. It's one of the most advanced and effective infill patterns you can choose for high-performance mechanical parts. It takes longer to print, but the results are simply on another level. So, how do you put this all together? You combine percentage and pattern to engineer the soul of your part. A decorative vase might be perfect with 15% lines infill, fast, cheap, and just supportive enough. A wall-mounted tool holder might need 40% grid infill for good, reliable strength. And that critical drone arm that cannot fail? You might choose 70% gyroid infill to give it maximum, multi-directional strength and impact resistance. Now, a crucial point for using online services. Some simplified services might just give you a choice like standard or high strength, and they're making these infill decisions for you behind the scenes. But more advanced services, and especially when you prepare your own file using Slicer software, give you direct access to these settings. Understanding what they mean is the difference between hoping for a good part and knowing you'll get a good part. You can communicate your needs more effectively. You can say, I need this part to be strong against torsional forces, and you'll know that a cubic or gyroid infill is what you're really asking for. This knowledge transforms you. You're no longer just a consumer of 3D printing. You're a participant in the manufacturing process. You're making conscious engineering choices about the hidden internal architecture of your design. You're deciding whether it needs to be light and fast or a fortress of durability. By mastering the interplay between infill percentage and pattern, you unlock a new dimension of control. You can optimize your parts perfectly for their intended function, saving time, money, and material while dramatically improving their performance. The outside of the part is what everyone sees, but the infill is its secret heart, its hidden strength. We've now reinforced the inside of our model, making it strong and resilient. But what about that outer shell? The surface that everyone will see and touch? How do we ensure it's not a rough, jagged landscape of visible layers, but a smooth, detailed, and beautiful surface? The quality of that finish is determined by one of the most fundamental settings in all of 3D printing, and it's where we're going next. That fundamental setting is called layer height. And understanding it is like learning the difference between a grainy, pixelated photo from a 2002 flip phone and a stunning high-resolution image from a modern camera. Both are pictures, but the experience, the detail, the quality, it's a world of difference. So what exactly is layer height? Imagine building a sculpture out of stacks of paper. Layer height is the thickness of each individual sheet of paper. If you use thick construction paper, your sculpture will grow very quickly, but the edges will look blocky and rough. You'll see those distinct steps. Now imagine using incredibly thin, fine sheets of vellum. It will take you ages to build the same height, but the final surface will be incredibly smooth, with curves that flow almost perfectly. That's precisely what's happening inside the 3D printer. The machine is laying down one sheet of melted plastic at a time. The layer height setting tells the printer the exact thickness of each of those sheets. A common layer height might be 0.2 millimeters. For reference, a standard sheet of office paper is about 0.1 millimeters thick. So we're talking about building your object 2 sheets of paper at a time. This single setting creates the most important trade-off in all of 3D printing: the eternal battle between quality, speed, and cost. You can pick 2, but it's very hard to get all 3. Let's break that down. First, let's talk about high quality. To get that beautiful, smooth finish, especially on curved or angled surfaces, you need a low layer height. Something like 0.1 millimeters, the thickness of that single sheet of paper. With layers that thin, the stair-stepping effect on a dome or a slanted surface becomes almost invisible to the naked eye. Each step is so tiny that they blend together, creating the illusion of a perfectly smooth curve. This is the setting you choose for detailed miniatures, for presentation models, for anything where the final look and feel is the absolute top priority. But here's the catch. To build a 1-inch tall object with 0.1 millimeter layers, the printer has to draw 254 individual layers. That takes a lot of time. And when you're using an online service, time is money. A longer print time means the machine is occupied for longer, so the service has to charge you more. So low layer height equals high quality, but it also means high cost and a long wait. Now let's swing to the other end of the spectrum. What if you need your part fast and cheap? Maybe it's just a rough prototype to check if 2 pieces fit together. Maybe it's a functional bracket that's going to be hidden inside a machine, and no one will ever see it. In that case, you don't care about a perfect finish. You care about strength and speed. This is where you choose a high layer height, say 0.3 millimeters. Using our paper analogy, this is like using that thick construction paper. Now, to build that same 1-inch tall object, the printer only needs to draw about 85 layers instead of 254. That's a third of the work. The print will finish dramatically faster, and because it's using the machine for less time, the cost will be significantly lower. The trade-off, of course, is quality. The layer lines will be very visible. Those stair steps on curved surfaces will be pronounced. It will look and feel like a 3D printed object. But for many applications, that's perfectly fine. Function over form. This leads us to the middle ground, the Goldilocks zone. This is typically around 0.2 millimeters. It's the default setting for a reason. It offers a fantastic balance. The layers are fine enough that the part looks good, but not so fine that the print time and cost become excessive. For the vast majority of projects, desk organizers, custom cases, general-purpose gadgets, a 0.2 millimeter layer height is the sweet spot. It's the reliable workhorse of 3D printing. So, how do you see this on an online printing service's website? They usually won't ask you to type in 0.18 millimeters. They simplify it for you. You'll likely see options like draft quality, standard quality, and high detail or fine quality. Now you know exactly what those mean. Draft quality is just code for a high layer height. They're telling you this will be fast, cheap, and the layers will be visible. Perfect for prototypes. Standard quality is your Goldilocks zone, your 0.2mm setting. It's the default, the best all-around choice for most common prints. And high detail is your low layer height option. This is for when you need that museum quality finish, and you're willing to pay a bit more and wait a bit longer to get it. Your choice here directly impacts the final bill and the quality of the object you hold in your hand. So before you upload, ask yourself one critical question. What is the purpose of this part? Is it a display piece? Go for high detail. Is it a functional part that just needs to work? Go for draft and save some money. Is it something in between? Stick with standard. By making a conscious choice based on your part's purpose, you're taking control of the process. You're not just clicking a button. You're making an engineering and design decision that optimizes for what truly matters to you. Now, you might be wondering why these specific numbers. 0.1, 0.2, 0.3? It's not arbitrary. It's tied to the physical hardware of the printer itself, specifically the nozzle, the tiny metal tip where the melted plastic comes out. Most standard 3D printers use a nozzle with a 0.4mm opening. A good rule of thumb in printing is that your layer height should be somewhere between 25% and 75% of your nozzle diameter. For a 0.4mm nozzle, that gives you a range from 0.1 to 0.3mm. This is why these numbers are so common. It's the range where the machine operates reliably and produces consistent results. Going below that range is possible with specialized equipment, and going above it can lead to sloppy, weak prints. So when you choose standard quality, you're really just telling the service to use their best practice setting for their standard hardware, which is almost always a 0.4mm nozzle printing at a 0.2mm layer height. So let's recap this crucial step. We've taken our perfectly scaled and oriented model, and now we've defined its very resolution. We've decided whether it's going to be a rough sketch or a fine oil painting. We've made a conscious trade-off between its visual beauty and the cost to create it. We've moved beyond just the shape of the object and started to define its character, its texture, its tangible quality. We've done almost everything. Our digital file is robust, it's scaled correctly, it's positioned for success, and its surface quality is defined. It is so close to being ready. But there is one final bridge to cross. It is arguably the most important decision of all, because it's the one that transforms our digital file from a collection of data into a physical object in the real world. It's the choice of the material itself, the very substance our object will be made from. All the preparation in the world means nothing if you print a delicate sculpture in a brittle material, or a structural bracket in a flimsy one. Choosing the wrong material can turn a perfect file into a useless, broken object. And making that final critical choice is what we'll master in the final part of this journey. So let's demystify this final crucial step. The world of 3D printing materials can seem like a chemistry textbook come to life, with an alphabet soup of acronyms: PLA, ABS, PTG, SLA, SLS, DMLS. It's overwhelming. But in reality, for your first print, you only need to understand the fundamental trade-offs between a few key players. Think of it not as a complex exam but as choosing the right tool for the job. You wouldn't use a sledgehammer to hang a picture frame, and you wouldn't use a tiny tack hammer to break down a wall. Materials are the same. They fall into three main families: plastics, resins, and metals. For 99% of first-time projects, you'll be working with plastics, so let's start there. These are the workhorses of the 3D printing world, extruded layer by layer like a super precise hot glue gun. The most common, the one you'll see everywhere, is PLA, or polylactic acid. Think of PLA as the prototyper. It's derived from plant-based sources like corn starch, making it more environmentally friendly than other plastics. Its biggest advantage is that it's incredibly easy to print with, which is why it's so popular. It holds sharp details beautifully and comes in a rainbow of colors, including specialty versions that look like wood, stone, or even metal. If you're printing a decorative object, a tabletop miniature, a non-functional prototype to check the shape and size of your design, PLA is your best friend. It's affordable and gives you a fantastic-looking result. But, and this is a huge but, it has weaknesses. PLA is brittle. Drop a thin PLA print, and it's likely to snap. It also has a very low melting point. Leave a PLA object in a hot car on a summer day, and you might come back to a warped, melted puddle. So for looks, a plus. For strength and durability, not so much. Next up is ABS, or acrylonitrile butadiene styrene. You already know ABS intimately. It's the stuff Lego bricks are made of. That should tell you everything you need to know about its properties. ABS is the workhorse. It's tougher than PLA, more impact resistant, and can withstand higher temperatures. This makes it ideal for functional parts, things that need to move, clip together, or survive a bit of abuse. Think phone cases, drone parts, or brackets for a shelf. The trade-off is that it's trickier to print with, often requiring a heated enclosure to prevent it from warping as it cools. But that's the beauty of using an online service. They have the professional-grade equipment to handle materials like ABS perfectly, so you get all the strength without any of the headache. If your part needs to be durable and take some stress, ABS is a classic reliable choice. But what if you want the best of both worlds? Enter polyethylene terephthalate glycol. It might be a mouthful, but think of it as the all-rounder. PTG is a fantastic compromise between the ease of printing of PLA and the strength of ABS. It's significantly stronger and more durable than PLA, but less prone to warping than ABS. It has a bit of natural flexibility, so it's less likely to shatter on impact. Many forms of PETG are also considered food safe, making it a popular choice for things like cookie cutters or custom kitchen containers, though you must always verify the specific materials certification with your printing service. It's like the material used for water bottles: tough, resilient, and slightly flexible. If you're not sure what to pick and your part needs to be reasonably strong, PTG is often the safest and most versatile bet. Finally, in the world of high-performance plastics, there's nylon. Think of nylon as the engineer. This stuff is in a league of its own for toughness and durability. It has a low friction surface, which makes it absolutely incredible for printing functional gears, living hinges, tool handles, or any part that needs to slide, bend repeatedly, or withstand significant wear and tear. It's incredibly strong yet flexible. The material in a zip tie is a type of nylon. You can bend it, twist it, put it under immense tension, and it refuses to break. When you need a part that is practically indestructible under normal use, you choose nylon. Now let's move into the second family: resins. These are used in a different type of printing, often called SLA or DLP, where a liquid photopolymer is cured by a UV light source. The defining characteristic of resin printing is detail. Insane microscopic detail. Standard resins are the sculptor's medium. They can capture features so small that you'd need a magnifying glass to see them. This makes them the undisputed champion for things like hyper-detailed miniatures for tabletop gaming, intricate jewelry patterns for casting, or architectural models where every tiny window pane matters. The finish is incredibly smooth, with layer lines that are often completely invisible to the naked eye. The downside: standard resins tend to be brittle, much like PLA. They are designed for their beauty, not their brawn. To solve that, there are tough and durable resins. These are the reinforced sculptures. They are specialty resins engineered to mimic the mechanical properties of plastics like ABS or PETG. They offer that same stunning surface finish and fine detail, but with much higher impact resistance and strength. If you need a functional prototype that also looks injection molded, or a final use part like a custom jig or enclosure that requires both a perfect finish and real-world durability, these advanced resins are the answer. The final family, the one that represents the pinnacle of 3D printing capability, is metal. Using processes like direct metal laser sintering or binder jetting, these services can create fully dense, solid metal parts from materials like stainless steel, aluminum, titanium, and even precious metals. This is not a metal coating or a plastic filled with metal powder. This is true functional metal. This is how you print custom car parts, lightweight drone frames, unique tools, or even medical implants. The strength, temperature resistance, and performance are exactly what you'd expect from a traditionally manufactured metal part. Naturally, this process is the most expensive, but it showcases the incredible power of this technology. To go from a digital file to a real functional metal object is nothing short of magic. So how do you choose? It's not about memorizing specs. It's about asking 4 simple questions. Question 1. Is this for looks or for function? If it's a visual model that will sit on a shelf, your primary choices are PLA for its cost and color options, or standard resin for its ultimate detail. If the part has to do something, you immediately look towards PTG, ABS, nylon, tough resins, or metals. Question 2. What environment will it live in? If it's going to be in a hot car or near a motor, PLA is out. You'd need ABS or PTG. If it's going to be outdoors, you'll need something UV resistant. If it needs to be food safe, you look for a certified PETG. The environment dictates the material. Question 3. What forces will it face? If it's going to be dropped or hit, you need impact resistance, so PETG or ABS is a good start. If it needs to bend without breaking, nylon is your champion. If it needs to be incredibly stiff and not flex at all, you might look at carbon fiber-filled composites, or for the ultimate in strength, metal. And question 4. What's your budget? There's a clear hierarchy. PLA and PETG are typically the most affordable. ABS and standard resins are a step up. Nylons and specialty tough resins are more expensive still. And at the top of the pyramid, you have composites and metals. The instant quote feature on these websites is your best friend here. You can select your model and toggle between different materials to see the price change in real time. Once you've answered these questions, you're ready. You navigate to your chosen printing service, you upload that pristine STL file you've worked so hard to perfect. You select your material from the drop-down list. Let's say you've decided on PETG for its all-around strength. You select your color. The website gives you that final price, that final confirmation. You do one last check. The dimensions are correct. The orientation is how you want it. The material is the right tool for the job. You take a deep breath and you click order. And in that moment, you've done it. You've bridged the gap between the digital and the physical. You've taken an idea, a fleeting thought in your mind, and guided it through the entire process of becoming a real, tangible object in the world. The feeling of unboxing that first print is something you will never forget. The weight of it in your hand, the texture of the layers, the realization that you created this. It's a powerful, almost magical experience. This isn't just about making trinkets or gadgets. It's about empowerment. It's the freedom to invent, to solve a problem, to create something uniquely yours that the world has never seen before. This series was designed to give you the keys to that kingdom. You now have the knowledge to take your own ideas on this incredible journey. This isn't an ending. It's the very beginning of your story as a creator, a maker, and innovator. You have the tools. You have the map. Now go make something real.